now is just repeat what I did for SL2 for specific sequence in this general setting. So I'm about to write down the Mautner phenomena again. So you can. This is a nice little lemma that is very useful, and you know. So think of whatever you want. Just be quiet. And if G's act on X by isometries, and you have A n X goes to X. I don't need X, little x, to be A n fixed, but I need these kind of dynamics. Then I get that X is fixed by the group generated by U plus and U minus, and obviously by the closed group generated by these. The stabilizer of a point is a closed group. So this is the claim, and the one line funny proof is more or less the same. Let me repeat it. For U say in U plus, we get that duxx now is not equal, but definitely is converges to I don't know. This sequence UANX converges to UX. This sequence converges to X, and the distance function is continuous in two variables. So we get this convergence, and now this guy over here is the same by invariance of the metric. And this piece here, by definition of U plus, over there, converges to 1. So this number, so this sequence converges to 0. But converges to this number, so this number is 0. For U and U minus, use the fact that if A n x converges to x, then also A n inverse x converges to x. More generally, if A n x converges to y, then A n inverse y converges to x. This is a stupid fact, but I am emphasizing it because this is a fact that does not valid in a general topological space. It is valid in metric space. Okay, fine. This is the lemma, and here is a small improvement. Or a small trick that comes naturally attached to this Mautner lemma. Assume an goes to infinity. Say somehow we are interested in interesting dynamics, and assume ANX goes to y. Then again, AN inverse y goes to x. But But what I'm claiming is there exists Bn in the group generated by the ANs such that.
And can you also consistently consider that this group generated is a closer of the group?
Well, my notation implies that yes, but by the proof you see that this is not needed. This is the statement, yes. I didn't say otherwise. Let's see the proof of this. Let's see the statement first. The proof is something very, very easy, such that Bn still goes to infinity, and Bnx goes to x. Whenever I have converging dynamics, I can somehow change a little the variable, so I'm having sort of the same point here. Let's prove this one. Let's prove it in this parenthesis. Since An inverse y converges to x, I'll use that. And fix a subsequence nk or ank such that ak inverse ank goes to infinity. Then observe that ak inverse ank x goes to x. So this guy will be my b. This will be bk. Let me explain again. I'm adding x. My sequence takes it to y. I can pass to a subsequence which is much sparser and converge much faster to infinity. It still goes to y, and come back from y to x in a lower speed. Okay, so think about it. It's not hard, and now what I want to explain is why. Well, in my example, where is my example? Is there? In SLNR, I wanted the dynamic, the AN sequence to be in the group A, in a diagonal group. The claim is that whenever you consider SLNR and a dynamics or a sequence tending to infinity, it is actually, in an essential way, happening in the diagonal group. And the reason for that, or the explanation for that, is what we call the KK decomposition. So up to compact noise on left and right, G is A. So this is a very important phenomenon in dynamics of groups, so let me explain this carefully. Let me start. Let me give a title. Let me start by considering GLM and explaining what. So I'm leaving our discussion of metric spaces for a minute. Bear this in mind, but be prepared to get some other stuff. The claim is that GLNR, this might be familiar to you, every element in GLNR could be written
by a product of three elements, an orthogonal matrix, and this is a positive diagonal element. Positive means that all eigenvalues are positive, and another orthogonal. So this is sometimes called the K, orthogonal, A, diagonal, K, decomposition of GLN, or polar decomposition of GLN. If you are familiar with the symmetric spaces, G mod K, then this is the fact that up to rotation, every element could be put into a flat. Up to the action of K on G mod K, you are a copy of A, or A plus. Actually, I can take this diagonal matrix, lambda 1, lambda 2, to be ordered. This is bigger than that and bigger than that. So I can take things from some semigroups here, but I will not use that. Okay, let me explain this. This is classical and of importance outside of our discussion. In any case, for G in GNR, I can think of G as a matrix and consider this matrix. This is, of course, symmetric. Think of it as a form.
What's T?
Transpose. Transposition. So this is G transpose times G. You can think about it as the inner product, the standard inner product for the basis given by the element G. So this is symmetric positive definite matrix. Means that this defines an inner product. It's another way to say the same thing. Hence, so basically we know that every inner product, the ball of every inner product, with respect to the standard inner product, if we think of it, is some ellipsoid. It has axes, orthogonal directions, axes of, I'm not sure how you call it in English. But, or if you wish, the thing is that I can phrase it in the sense that every positive definite, or actually every symmetric matrix, I can diagonalize by orthogonal matrices. Hence, there exists K in ON, an orthogonal matrix, such that, so this means that K inverse equals K transpose, right? This is orthogonality. Such that G transpose G, K inverse or K transpose, doesn't matter, is, well, positive diagonal. And let me write it down specifically, let me give a name so you can think of it as lambda 1, lambda 2, lambda 3, lambda n. And these are all positive numbers, and they have square roots. I can take the square root of that matrix. So this is A squared. A, again, positive diagonal. And obviously A equals A transpose. So, G transpose G equals K transpose A transpose A. And now I'm defining a new guy, K prime. By the following formula, this will be G K inverse A inverse. And I claim that this guy is orthogonal as well. So I claim that if I take the transpose of K prime, sorry for doing this computation in front of you, but this is an important piece of math. Okay, now this thing in the parentheses here, I will write differently using that formula over here. This G transpose inverse K transpose A transpose. So inside the parentheses, I used change coming from here. And now I'm just making the transposition, reversing the order as I should, right? And this is AKG inverse which is GK inverse A inverse inverse which is K prime inverse. I was showing that K prime transpose is K prime inverse. And K prime is as well in omega. And you get, by definition of K prime, that G has this decomposition as claimed. I took an arbitrary element of GLN, G, using the representation of it, or using the fact that it gives me a positive definite matrix, G transpose G, doing the polar decomposition, I found the essential positive square root of it represented in the KK decomposition. Okay, I did it for GLN just because it is easier to prove somehow, but I get it right away for SLN. And I didn't introduce the KK notation over here just because I wanted to reserve it to SLN. We already explained what A is. A is diagonal matrices, but with determinant 1. And K is SO. So, why? For any G in here, I'm proving it now. For any G in here, G could be written as KA, K prime, as an element of GLN. Now, the determinant of G is 1. But it equals the determinant of K, determinant of A, determinant of K prime. K and K prime K and K prime are orthogonal, so the determinant must be a root of unity, or the eigenvalue is a root of unity, it must be real, it is plus or minus 1. And since the product of these three things is 1, it means that the determinant of A is plus or minus 1, but by positivity, determinant of A is 1. So this A in the decomposition is in SLN, as we voted. Maybe K and K prime are not. Maybe the determinant are both minus 1. But then I can take minus K and minus K prime. And this will be a good decomposition. So change K, K prime to minus K prime, if necessary. If necessary. To get the composition in SLN. So this decomposition, after maybe a change of sign for the case, is a composition in SLN. Okay. So now, what happens now? I think I want to hide this. I want to prove the theory. I'm still not used to work with a wet palette, so I don't think why is it?
Excuse me, when you multiply by minus 1, then the determinant is multiplied by minus 1 to the power n.
Oh, I didn't think about it. Okay, so it's an exercise to improve my computations. I was sloppy, sorry. Thanks. Okay. So we still need to improve the KK decomposition, but I will use it for SLN. It is still valid, and using it, I will prove the term that appears up there. Okay. So I'm having an action of G on X, preserving the metric, no fixed point, and I'm assuming it is not proper. So I did erase, I mean, we still have the definition of what a proper map is, but I did erase the equivalent condition. I will use the third one. So this means there exists xn which converges to x and gn which converges to infinity such that gnxn converges to some y in x, does not converge to infinity. Upon passing to a subsequence, I may convert. I mean, converging to infinity means that you don't have subsequence, a converging subsequence. I do assume that This guy does not converge to infinity. I'm passing to a subsequence to make it converge to y. Some y in x. Write Gn to be k and an kn prime according to the k decomposition, and somehow there is no dynamics in the k's, all dynamics is in the a. So this is the principle that I'm illustrating. Without loss of generality, Kn is converging to some k, Kn prime is converging to some k prime. Again, I'm passing to subsequences. This all is happening in k, and it is an that must go to infinity. Now, from this you get easily that an k prime x does converge to k inverse 1. Or if you wish, an k prime x converges to y, and k prime inverse it. And from this, so now, here is a point, here is another point. These guys are in x. These are the x and the y that you see here. So maybe I should change my an sequence, converge to infinity, to some other sequence, bn. Still living in big A, still converging to infinity. Okay? And then I could assume that I'm having another sequence that taking same x to same x. Now this x is this, I think, k prime x that appears there, but never mind. I'm having a sequence in big A, taking it to infinity and taking a point to itself. And looking here and see that this point x should be fixed by u plus and u minus. K prime x is u plus comma u minus fixed. But do we have it on the board? I don't know. This important moment. Showing how much capable I am to plan ahead. No, we don't. Ha! But this is SL and R, and this is contradicting the assumption that there are no fixed points. And the theory is proved. Okay? Any question?
So it's essentially a fixed point here.
It is essentially a
If
fixed
you
point.
have an interaction of SL and R, then it has a fixed point.
Yes, you may say so. And also it gives us the, okay, so corollary. For every action of R, of SL and R, isometric with no fixed point, the point stabilizers are compact. Just apply, I think, the second condition of properness. 2 points. And the orbits are closed. I will leave it as an exercise. You should know that the proper map is always a closed map. The image of a closed set is a closed set. In fact, more than that. In fact, the orbit space, I can always, whenever I have an action, g on x, I can look at the space of orbit, x mod g, and I can take the quotient topology. Usually, the quotient topology is very ugly. The action is called tame if the quotient topology separate points. This means that the orbits are locally closed. But here we have more than that. The orbit space is Hausdorff. Again, this is a small exercise about proper actions. There are various, okay, so this is what I wanted, this is the main part of the lecture today that I want to show. There are various generalizations of this which I want to discuss. Here is one. I will state it as a remark because I will not prove things, I will not explain everything to the end, but upon understanding the notions, what I'm about to say is very easy. What we did prove here is something about actions of SLNR on metric spaces, isometric actions. But it's not the metric that we used, really. It's the uniform structure that the metric gives. So I think that not everybody here knows what a uniform structure is. But I'll explain what it is for the metric uniform structure. For every given epsilon on a metric space, given a metric space, and given an epsilon, I can look at the set of all points, all pair of points of distance less than epsilon. This is a subset of x cos x. It's kind of a better notion than just a ball. It's the union of all balls. It's a relation. It's the epsilon distance relation on a metric space, and a uniform structure is actually a collection of relations on a space with some properties. The properties, well, you want this collection to be a filter. You want whenever you have a set in the relation, a set in the collection, relation of x cos x, every set that contains it will be there. You want the finite intersection of relations to be there. This means that basically you can take the minimum of finitely many epsilons, or the intersection of balls, and of course, I forgot to say, you want all the relations to contain a diagonal in x cos x, and lastly, but very important, you want some sort of an epsilon half argument to be applied. So whenever you have a relation, say u in x cos x, you want v in x cos x such that v times v is in u. When this is all xz such that x So we should think of this V as some epsilon half ball. And using this and translating all the sequence notations, typically this is not so good. I mean, this is not necessary, this language for metric spaces or metrizable spaces. You need it for non-metrizable spaces, but it is very useful notion. And using this, we can state differently the theorem, saying that for every equicontinuous action on a uniform space with no fixed point, the action is proper. Actually, more than that, the action is universally closed. Slightly improved notation. And why am I stating this? There is an important example of a uniform relation on a space. If you take a topological group, any topological group, you can think of the left uniform structure on it. The left uniform structure is for a group A. Take, U is not good, omega, and identity neighborhood, and consider now U will be all the xy's such that y inverse x is in omega. All the pairs of elements which are omega close to each other. If you think of omega as an epsilon ball around the identity, then this is the same, similar to the metric structure. And so there is left and right uniform structure on a group. Sometimes they are the same, sometimes not. I have no idea which one I wrote here. And, but the left structure is preserved by the right action, and the right structure is preserved by the left action. These are easy exercises. And just stating this, repeating the proof that I gave, you get this wonderful corollary of this discussion. For every topological group A and every continuous homomorphism S and N R and to H, the image is closed. Just think of the image of G in H and consider the right action of G on H. It preserves the left uniform structure. The right action of H on H preserves the left uniform structure, so is the right action of G on H. So it fits in here in the slightly changed formulation of that theorem, and the orbits are closed. The image is just the orbit of the identity. The orbits are closed.
G act on H?
By G, and it acts on the right side. The image of that homomorphism is the orbit of the identity. So this is a very powerful theorem. It applies for every target. Just let me remind you that for Z, this is not the case. Irrational rotation is a homomorphism of Z into the circle. Irrational foliation of the torus by lines is a homomorphism of the real line into T2, into the two-dimensional torus. So we know, when we discuss this for algebraic groups and algebraic morphisms, the image is always closed. But this is a very specific situation, and now here this is very general and very powerful.
How old is this observation?
Sorry?
How old is this remark?
I'm not sure. For SLNR, this was stated, I think, but under first compatibility assumption by Omori, I think in the 80s. Without this, and in the right generality, which I didn't express here, for all simple groups over every local field, this appears in a recent preprint that we have with Zahegelander. So this, not in that generality, but in the right generality. Maybe I try to check, because this should be classical, but I couldn't find a good reference. Now I want to do some to think about the proof that we had examination. Not of this last remark. To see what we used. We used only. Now I'm examining SLN. I'm trying to see what properties did I use when I proved it, and try to make some remarks about other groups that have the same properties. And then to say, without giving all the details, hey, the theorem should apply to this and that as well.
So you are examining the truth of the main theorem?
Of the main theorem, yes. So we use very heavily the fact that we had this A inside G such that 1, G could have been written as KAK for some compact. It was a group, it actually doesn't matter. Set K inside D. And so some of the dynamics is taking place in A. And this A had this nice property for every sequence AN in A tending to infinity. There exists a subsequence, so I write it in this sloppy way, up to a subsequence. U plus is non-compact, and the group generated by everything all these three groups that we consider is G. Conclude G as above, having these properties, is acting continuously and isometrically on a metric space, XD without fixed point, then the action is proper, almost correct. The points need not be fixed by all of G, it need be fixed by U plus and U minus, which is normal in U plus, U0, U minus, which generate all G. But maybe not BG itself. Maybe G is not simple as SLN. Maybe it's semi-simple. Maybe it's just one factor. Without point fixed by non-compact normal subgroups. So for example, and I'm about to write it down in a minute, if G is semi-simple, but not simple, then you can say only things up to point fixed by factors. If G is a simple group, everything I said just applies. Examples, which I will not prove. All semi-simple groups satisfy this. The assumptions they have KK decomposition with this kind of nice behavior of A, hence the conclusion of the theorem, as stated above. Another class of examples, all, if you care about those things, all tree groups, so groups acting on regular trees, which are nice enough or rich enough to act too transitively. On the boundary. Another class, kind of related, on groups acting strongly transitive on an affine building. So those kind of groups satisfy the theorem, and actually satisfy the version of the theorem about uniform structure, which I didn't state, and also satisfy this remark. Okay, I have plenty of other things to say, but maybe it would be nice to end the class in time today.